So thank you, Chris, and can I give you the warmest welcome to this public event? There are people of all ages here, so very much see this as a discourse where we can all join in. I just want to pick up a little bit further about Faraday. So this is a collaboration, this event, between the Faraday Institution and the Royal Institution. And Faraday was an extraordinary man. So he had very little formal education, and yet he went on to be absolutely at the foundation of inventing the electric motor, inventing the foundations of electrolysis, which is very much part of batteries, which is what this event tonight is all about. He was absolutely at the heart of electromagnetism, discovering how electromagnetic induction worked, which led to motors and so on. But actually, here is a man with very little formal education who did everything from chemistry to physics, actually to engineering, translating science into real application. So it's absolutely amazing to be in this room, because this room Faraday stood in 200 years ago when he founded the Christmas lectures, but indeed before that, within this building, many of his most famous inventions actually took place. So it's deeply symbolic being here tonight. So this event tonight is about engineering the skies, the rise of electric flight. I'm Deputy Vice-Chancellor at Cranfield University, and for those of you who haven't heard of Cranfield, Cranfield is purely postgraduate, and it's the only university in Europe with its own airport, its own aircraft, its own pilots, and its own air traffic control services. And so aerospace, and therefore electric flight and sustainable aviation, very much at the heart of what we're doing. So, as we look at the challenges around electric flight, which is where we're at tonight, we need to just ground ourselves for a moment. So, aviation fuels. Most flight nowadays is based on kerosene. And the thing with kerosene is it's like sometimes people call it aviation fuel, just as a general term. But kerosene is quite a good compromise between the energy density and how much space it takes up. So to get our aircraft into the air, we're going to need a certain amount of power to overcome the weight. Within our fuel, we've got to get that power density, that energy density that we actually need. But when we look at some of the competing ways of powering flight, there are some very big challenges. So some people tonight, our speakers, may actually refer to hydrogen. Now, hydrogen is an alternative way of getting to zero carbon fuel, and it's got great energy density per kilogram, but it takes up a lot of space. So when people are looking at aircraft to get across the Atlantic, and I'm sure Jacqueline, who's one of our speakers, is going to talk about this, it's actually really difficult to have an airliner that actually can get enough gaseous hydrogen on board to get across the Atlantic. Then let's look at what happens with batteries. So a lot of tonight is about batteries, getting electric flight. And we need our battery density, its energy density, to be really high and for the battery not to weigh so much. And that's a big challenge, because you'll know for automotive battery applications, electric cars, one of the big challenges is the weight of the battery. So many of the researchers who are in this room tonight are people who are real experts on trying to drive forwards how do we get batteries of sufficient energy density but also at minimal weight to actually get on board. So just a few examples before we move through to the speakers. This is an electric aircraft. It was designed and built purely by British researchers and design authorities and manufactured actually by British manufacturers. And test flights by a Cranfield academic who is also a qualified test pilot. As an illustration of the challenge around electric flight, our test pilot had to lose 2 stone in weight. So this is real sacrifice on his part. Guy Grattan is an absolute star, but has done a number of test flights now with this. It's called the eCub. It was funded by Innovate UK, so our thanks to Innovate UK, but a real celebration of British design, British manufacturing, and British test piloting. Now, you're going to hear more from Lim Hai later on about vertical aerospace. This is an example of an electric vertical takeoff and landing aircraft. I'm looking at Lim Hai to make absolutely sure I've described it correctly. But you're going to hear a lot more about vertical aerospace later on. And then this, if you wanted to go and buy now an electric aircraft, the one that is on the market and fully certified and ready to go and already being used in flying schools is the Pipistrel. And the Pipistrel, I think it comes from Slovenia. I'm looking at Limai, who's probably expert on its country of origin, but I know that there are flying schools that are actually using this. It's a 2-seater electric aircraft. So a trainer aircraft, and the RAF, for example, very involved in looking at the future of training pilots using small electric aircraft. And then this is a concept aircraft, not yet tested, not yet in reality, but it's an aircraft for search and rescue, and the concept is that it will be autonomously flown, but with the emergency first responder actually on board, and then they would be delivered to the site of the accident by this autonomous vertical takeoff and landing vehicle, electric powered. Now, this is a competition. This concept aircraft is involved with a competition where there have been 200 entries. 10 have been selected to go through to the next stage, which involves moving towards the actual real operation of an aircraft. But this is the UK entry into this competition, which has been selected to go through to the next stage, stage 2. So 1 of 10 in the whole world for this challenge around search and rescue. So by going autonomous, it does have a remote pilot able to come in if necessary, but by going autonomous, you can remove the need for the pilot, and therefore you can get more of your emergency response weight, both the emergency responder themselves and their equipment, actually on board. And you can see how slim it is as a design to try and get that weight requirement actually down. So, with no more ado, I'm going to introduce Jacqueline Castle, who's our first speaker tonight. Can I just highlight for everyone that we're going to save questions for the end, so we'll go straight through our 3 speakers, and at the end I'll invite the speakers to come up to the front and we will take questions. And for those of you who are online, please can I encourage you to put questions into the question feed, and then they'll be fed to us when we get to the panel session at the end. So Jacqueline, who is a Fellow of the Royal Academy of Engineering, and for those of you who aren't aware of how important that is, being a Fellow of the Royal Academy of Engineering is the highest honour for an engineer in the UK. It's the engineer's equivalent of being a Fellow of the Royal Society, so an amazingly high honour. Jacqueline is the Chief Technology Officer of the Aerospace Technology Institute, which is a major institution, major government-funded body, to really ensure that UK aerospace remains at the forefront of global aerospace and firmly on the path to a sustainable future. Before joining ATI in 2023, Jacqueline spent her almost entire career actually in the industry, particularly with Airbus, most recently as the UK chief engineer for the Airbus A320 family of aircraft, which is one of the most important families of the Airbus family. with responsibility for the wings, the landing gear, and the fuel system. So when Jacqueline comes to talk to you, she's talking to you from real hands-on experience of getting things in the air, approved, certified, and you know, one of those aircraft that we actually do fly in. So welcome to the stage, Jacqueline.
Thank you, Helen. Thank you. Thank you very much, and good evening, ladies and gentlemen, and thank you for this opportunity, because it's a real honour to be here to discuss battery applications on aircraft and the technology developments for the future. So, after all, aviation faces a global challenge at the moment. Air traffic is at record levels, and demand for flight is increasing again following the pandemic and the recovery from the pandemic, and that's leading to a huge backlog of orders for new aircraft. So whilst this growth is a fantastic prospect for the sector, and aerospace is a key sector in the UK, this growth must be delivered whilst reducing emissions to achieve aviation's net zero 2050 goal. So removing aircraft emissions will require multiple solutions working in parallel. And as the graph on the right-hand side shows you, there are a number of different routes to try to get to net zero. And one of the starting points is to replace the fleet with today's 20 to 30% more fuel-efficient aircraft, which you can do now, but also then to use more sustainable aviation fuels. But that requires a significant ramp-up to produce the quantities necessary. Other improvements could be made to flight operations. But even with all of these items, there's more to do, and future technology has a really big part to play. Striving to make the next generation aircraft as efficient as possible to directly reduce the fuel that's used, and thus the emissions is generated, is really key. So developing aircraft to use revolutionary fuels as well, like liquid hydrogen, as was mentioned, can also help us deliver zero carbon emissions. So there's plenty for us to go at. Let me introduce the ATI for those of you that are aware. So we're a private, not-for-profit company, and we're working independently to advise UK government on aerospace technology development needs. We manage 3 ATI funding programmes, and to date, the ATI has directed 3.6 billion of funding from UK government, matched by industry, with a future commitment of 195 million per year out to 2030. The ATI team provide expert analysis, models and tools to inform how technologies may integrate together and the sustainability benefit that they will then deliver. And the tools are available through the ATI website if you want to take a look at those. And they assist stakeholders in their technology benefit assessments. Our own independent modelling includes economic, market, sustainability, and aircraft-level technology modelling. And we reflect the ATI's project portfolio onto our concept future aircraft models that can then be used to trade technology routes and give a basis for sector discussion and thought leadership. We also convene the sector through technology advisory groups, communities of practice, showcases and events, including our annual conference. So the applications for funding are made on a rolling basis, and we have 3 full-stage application gates per year. And the technology is assessed against the ATI's technology strategy that you can see on the screen here. And this guides the UK sector to the areas that are necessary to grow the UK's market share and move the dial in sustainable flight. So the technology strategy, Destination Zero, contains 3 roadmaps. It has an ultra-efficient technologies roadmap, a zero-carbon roadmap, and also a cross-cutting technology roadmap. And all these 3 areas play a part in growth and net zero. So we need the most efficient vehicles in terms of aerodynamic performance, in terms of propulsive performance, and lightweight airframes and systems to minimise the fuel that's needed, whatever fuel that might be. And we need a revolution in technology to achieve true zero carbon flight. And we must deliver this in all of this in an operationally and cost competitive way. So the ambitious production rates of the future require highly automated, digitally enabled, high quality industrial processes. and products will use these advanced novel materials and processing techniques in order to achieve the efficiencies required. So the roadmaps capture all of this ambition. So we're here tonight to focus on the use of batteries in aircraft and what more we need to do to bring battery flight to the skies. And today, batteries are used in two main ways. Firstly, to power some systems on large commercial aircraft, excluding propulsion itself. And then secondly, to provide propulsive power for very small aircraft, of which there are very few certified platforms. And Helen mentioned one of them, the Pipistrel Velis Electro. So as was said, the first certified electric-powered aircraft, fully approved and mainly used for pilot training. And it has a 57 kilowatt liquid-cooled electric engine, which provides power to the aircraft. And the power is delivered via a 345-volt DC electric system built around a liquid-cooled high-performance battery system. So Pipistrel has two batteries connected in parallel, and they're installed in a redundant two-unit arrangement with a total nominal capacity of 20 kilowatt hours. So there's one small example. The lower picture is an experimental racer aircraft, the Spirit of Innovation. And this was developed under the ESSEL project supported by ATI funding and led by Rolls-Royce. And this has Electroflight's battery and powertrain and YASA motors, and the aircraft was propelled by a 400 kilowatt electric powertrain and the most power-dense propulsion battery pack ever assembled for aerospace at the time. It has more than 6,000 cells in the battery pack. It also had YASA's F1-styled axial flux motors, and it achieved 3 speed records. But more importantly, it provided important data for all involved, and that's primarily relevant to the applications that will be on all-electric urban air mobility projects in the future and hybrid electric commuter aircraft. So those are a couple of examples, and as we said, there's not many small aircraft certified at the moment. But on current latest generation large aircraft, like the Boeing 787 and also the A350, batteries are primarily used for APU start and ground operations when the main engines are off. They're also used for backup functions during flight, such as primary flight controls, avionics, lighting and fuel pumps, and some anti-icer systems. And the most modern batteries on those aircraft are lithium-ion chemistry, and the Boeing 787 has 2 battery packs, each with 8 cells, producing 32 volts DC, and it has 150 amps when starting the APU. A350 also has a lithium-ion battery as well, but it also has a smaller nickel-cadmium battery, and really that's quite old technology now, also used on many other aircraft, such as older Boeing 777s. But that's less powerful, more heavy, much larger, hence the drive to move towards more advanced lighter weight battery chemistries. So on what will happen really for next generation large aircraft? So the next generation aircraft are aiming for at least 30% fuel efficiency improvements, most of which will come from the airframe and from the engines. So further improving the aerodynamics with longer, leaner, lighter weight wings, like you see in some of the pictures here, and also the inclusion of higher bypass ratio engines, such as Rolls-Royce's development engine UltraFan, which is targeting a 10% improvement on previous generation engines, or CFM's concept engine RISE, with the open fan architecture, which is shown in the Airbus schematics on the slide. However, these future aircraft will also push for advances in electrification on board and require greater battery power for these increased functions. So primary battery use, in addition to APU or ground ops, is likely to include electric taxi functions. And this would enable the aircraft to taxi from the stand at the airport out to the runway without the engines running, and as well as when the aircraft lands to be able to taxi back into the airport spaces. So this would be beneficial for both sustainability and local air quality reasons. And potential hybrid propulsion applications may also require batteries, but I'll cover more of that in a moment. So other backup functions during flight, in addition to primary flight controls, would include avionics, lighting and fuel pumps that are already on the aircraft, could include secondary flight controls, such as the braking system, the environmental control system, cabin systems, and perhaps other landing gear functions. So even a small number of these additional functions will lead to a substantial increase in demand for aerospace-grade batteries, which is orders of magnitude higher than today. If we turn now to pure battery electric propulsion, as shown in the diagram here, the batteries are powering electric motors that are then driving one or more fans to propel the aircraft. So it's probably as simple as you can get. In the UK, there are exciting developments in electric powertrains, and Safran has recently certified their ingenious motor technology in a world-first EASA CS23 certification. So this technology was developed with support from the ATI APEC project, and we can look forward to production at their UK Pitstone site with applications for motors initially on small aircraft, similar to the Pipistrel, as well as for eVTOLs. But pure electric propulsion developments today are mostly aimed at the eVTOL market. And whilst the flow of energy from the battery to the motor and to the fan might be pretty straightforward in principle on a piece of paper, there are many challenges to overcome. But here in the UK, we have a number of organisations working in this area, with Vertical Aerospace being the most advanced. And you'll hear more from them next, and how they're developing their battery packs for their full-size VX4 prototype, as you see at the top left in the picture. And that's during initial piloted tethered testing, but I know they've made much more inroads now in their flight testing, so I'm hoping we'll see and hear more about that in a moment. But one of the main challenges with pure battery-powered vehicles is managing the weight of the batteries as the percentage of the overall vehicle weight. And obviously that's being able to then deliver sufficient useful range. Recent startup Sora is also looking at their concept for an eVTOL bus, which is aiming to increase the people carried. And there are also sub-regional scale aircraft that have been aiming for fully electric flight. Heart Aerospace, a Swedish electric airplane maker, shown bottom right, is one of them. On their project, BAE Systems are collaborating and will define the battery system. But we are seeing that both eVTOL and especially regional concepts are finding that the battery energy density challenge is significant. The fact that the battery energy technology today is still very heavy means that hybrid electric solutions may be necessary instead of pure electric. And a number of key players have recently announced hybrid proposals as range extenders. In other words, they may design the vehicles to be purely battery-powered for short distances, but have either a hydrogen fuel cell electric or conventional small gas turbine engines also on board, available for longer flight operations. So it's clear that the current weight of battery packs, and therefore their specific energy capability, negates the opportunity to scale beyond small aircraft without significant developments in fundamental battery chemistry. And given the current forecast for battery-specific energy and its influence on aircraft usage, this means battery demand in aerospace applications is a lot lower than for other sectors such as automotive. So automotive developments are now primarily focused on cost reduction. So it's really key that the aerospace sector keeps raising the profile of its battery use cases to ensure that future battery technology developments are also shaped by aerospace requirements, and the ATI is aiming to do as much as possible to support this messaging, including working very closely with the Faraday Institution on this. So not wishing to steal totally the thunder of the next presentation, but the work Vertical Aerospace is doing under their ATI-funded category-enhanced battery development project to develop key design, manufacturing, training and qualification capabilities so that we can have competitive UK production of primary propulsive battery systems is really a highlight of the aerospace battery work that we've got in the ATI programme and in the UK itself. I mean, typically here we're focused less on the cells themselves, but instead on integrating the high-grade, mass-produced cells from abroad into highly sophisticated battery packs designed specifically to address stringent safety needs of aerospace applications. So obviously, aerospace will need both revolutionary battery chemistry advances as well as packaging innovations to address all of the challenges it faces. So if we turn now to what electric propulsion options there might be for commercial aircraft, large commercial aircraft, what can we do? Now, the most promising option being looked at for next generation aircraft in the next decade is the addition of hybrid electric power in the form of parallel hybrid arrangements. And in its simplest parallel hybrid system, a battery-powered motor and a traditional fuel-based engine are both mounted on a shaft that drives the fan. So either one or both can provide propulsion at any given time. Now, the additional energy provided by the battery-powered motor means that the gas turbine's combustor can be more efficiently sized with a smaller core, reducing the engine weight and fuel burn, thus reducing carbon emissions. Now, there are a couple of likely ways that parallel hybrids might be applied. They could be either by boosting the gas turbine during takeoff and climb, and a parallel hybrid system could provide around 10% of the propulsive power during these phases. Or alternatively, with motor generators perhaps on both the low and high pressure shafts of the gas turbine to allow power sharing between the shafts. And in this arrangement, batteries would be required to manage transient loads. Successful implementation will require a positive trade of additional weight by adding the hybrid system components versus the weight reduction and reduced fuel burn that can be achieved by the gas turbine. So studies will indicate that about 5% improvements are potentially possible. So the system would need to address other aerospace-specific requirements like higher altitude operations, but there are great progress being made and many studies actively, globally, that are looking at these options. As you can see on the left-hand side here, the RISE engine, the SWITCH project that Clean Aviation are funding, projects with NASA's electrified powertrain flight demonstration, and closer to home, Rolls-Royce have run ground-based testing as well. So if we look ahead, finally, to the possible future that we might see for electrification if we can progress some of these advances in electrical systems. This is NASA's N3X concept aircraft. It's got a blended wing body. It has a sleek design, which is helped by having these multiple distributed propulsive fans at the rear of the aircraft. And this arrangement is another sort of flavour that hybrid electric could take. On this concept, the generator engines are at the end of blended wings, and this unlocks the ability to adapt the airframe to a design like this, so you can maximise aerodynamic efficiencies, minimise the combustion engine use, and it really could be game-changing for the future. And coming back to Helen's point at the start, it could also be suited to hydrogen storage and fuel cells that would lead to a fully zero carbon emission flight. So I hope this has shown that there are multiple strands to the rise of electric flight. There's a rich and dynamic research environment all working to overcome the many challenges to deliver an electric revolution. So thank you very much. Thank you.
So if I could introduce our second speaker, this is Dr. Limhi Somerville, who is the Director of Engineering at Vertical Aerospace. Vertical Aerospace is a UK-based company developing electric vertical takeoff and landing aircraft. Limhi's expertise spans electric propulsion. He previously led on powertrain and battery systems development at Vertical. I wanted just to draw out your involvement in European standards as well, Limhi, because these standards, in order to fly a novel aircraft, you have to go through a whole program of satisfying certification with the relevant certification bodies, both UK, European, potentially US as well, and indeed other parts of the world. I know you've been very involved in developing particularly European electrification standards for aerospace. So it's just a really important point about the commitment to developing standards in what is a very novel area. And I know you went to Vertical from Jaguar Land Rover, where you worked on the I-Pace, so you're actually an expert on lithium-ion batteries as well. So over to you, Limhi. Thank you.
Thank you very much for that introduction. It all sounds rather grander than it was. But I just wanted to, first of all, there's two things, a warning, I suppose, to begin with, which is whenever I'm very excited about something, I talk very fast. And whenever I'm nervous, I talk very fast. So this evening, good luck trying to keep up with me. I'm not completely certain where we're going to go or if the talk I give you is actually the one that I started off with. I wanted to start talking about time. So Vertical Aerospace was founded by someone called Stephen Fitzpatrick. And essentially, he owned a Formula One team at the time, and he came into Brazil to go to Sao Paulo, and he landed at the airport, and he did what most of us would do. He'd never been to Sao Paulo before. He jumped in a taxi, and he tried to get to the Formula One game. And hours ticked on, and he sat in traffic, watching helicopters fly over his head, going to the Formula One. And he missed the entire game, didn't get to see his team, arrived well afterwards, and then, of course, came back and whatever else. And a few things stuck with him. One was whether or not he could do it. That's something that entrepreneurs tend to have. But there were a few other things. One, could he do it with a little less noise? Helicopters make an awful lot of noise. Secondly, could he do it with a little less pollution, or a lot less pollution? And finally, could he do it with a little less cost? But fundamentally, at its core, in all of those other things, is the saving of time. Here we go. So let's come away from Sao Paulo for a brief moment and start to go to somewhere a little bit closer. So imagine you're going from Battersea to Heathrow. In fact, I was doing some driving in London today, which is novel for me, and it did take a very long time to go anywhere. So, but best case, without a lot of traffic, we find ourselves with 52 minutes if we're going to take the car, 65 minutes if we want to take the rail, and 8 minutes if we wanted to take a helicopter. In our case, a very specific type of helicopter. So this is a multi-rotor. Here we go, we've got some more animations for you. In this particular case, the helicopter has a distributed electrical system, which is the main advantage of an electrical system, multiple motors. You would be able to come onto that, go through security, imagine security in a sort of downtown, finish it out of your hotel, go to the roof, go through security. For anyone, I'm about to catch a flight tomorrow. I give myself about 2 or 3 hours buffer, depending on traffic, security, and everything else to get through. The concept being that the amount of time that we save. When we do that, we fly in airside, we get off, we go onto our aircraft, the aircraft that we're going long haul. So these types of aircraft is a real sweet spot for battery technology, predominantly because the larger they become, the more power you end up with, and the batteries just aren't light enough. Whereas they can really work in a condition like this. I'm going to have to check my notes, make sure I've covered off all the points. They really do work. Now, you've seen a lot of renders, and so I wanted to show you something a little bit more real, so I'm going to be quiet.
Test B2. Oh, ready to go. Tango officer.
Controllers go for takeoff.
Accelerating.
Continue.
Good, and decelerating now.
Plow on ground.
Test out. Good job, everyone. Thank you.
Okay. So, it's pretty cool. I've got to tell you, when you see it in person, it's pretty cool. And I'll give you an example just quickly from a flight test. I work with a whole series of, when I was a child, we would have called them like plane anoraks, the people that sort of spotted planes. I work with people that design planes, right? So they spend a lot of time spotting planes in the sky and go, oh, I did the landing gear on that, and there's a really novel feature on this thing that sort of... And so we're all stood there, we're watching the aircraft, it's hovering, we're talking, we're about 50, 60 meters away. And suddenly we just hear a slight whining, and then over the top of the hangar comes a traditional sort of 2-seater turbine helicopter, relatively small sort. I kid you not, we had to physically stop talking with the noise, this sort of whoomp, 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 that finds itself from the helicopter as it lifts over, and we see that and it sort of comes down. And there's a few things that drive that, right? You'll notice on this particular aircraft. So on a traditional helicopter, you end up with a lot of tip speed. And what that means is it drives a lot of noise. So as a consequence of the tip of the rotor traveling so fast, you end up with a really, and also it just comes at a certain, I mean, you all know helicopters when search and rescue or something like that's going over the top of you can hear this noise. It's just not the case. So the reason for that is we distribute that thrust across multiple systems, the advantage of electrical propulsion, and by distributing that thrust, the speed reduces drastically. And you also find that it just sits in a slightly, I don't know how but it's sort of different perception in terms of where that noise sits. So it's less irritating when you listen to it. Now, of course, right at the center of that is the battery, which I will come on to now. When I first started at Vertical, I actually got hired just to work for 12 months to find someone else to give us a battery. So that was the job, actually, was come on over and just spend 12 months and find someone. And we spent about 6 months looking for someone, and then we couldn't find anyone that was, because we're right on the edge of what the battery needs to be capable of doing. And so we decided to bring that in-house. In fact, our head of battery is in the audience with us today as well from Vertical. And most of what I'm about to show you is actually done by Chris Liner, so I should just caveat that before we go any further. But first thing to note is that there are just so many requirements. You touched on the certification standards. I was just going to read them all to you today, but I thought we might do something slightly less boring. So I've just picked 4 of them, okay? And we're just going to focus just on 4. The first one we'll save till the end. It is the most boring of all of them. It's just sample size, okay? It becomes significant. Secondly is fire containment. Everyone thinks about fires and batteries, and we all see the videos of various cars on the roads and those problems. The next one is something called state of function. You might refer to it as state of charge, but it's got some temperature considerations in there, so we call it a little different. And finally we have quite an aggressive drop test. It's novel for battery systems generally, and so we have to try and sort of compete with that. The other thing just to note is there's lots, of course there's other things. So you could talk about mass. I sat in a meeting once. In a previous battery design before Chris got involved and made them better, we had lots of these tiny little titanium bolts. And I was sat in one of our meeting rooms with a company talking about the cost and precision of drilling out the center of the bolt because we didn't need that bit of the mass. I can't tell you how expensive it is to drill out the center of a titanium bolt. So it's a very niche area of battery work. You would have not got them in the room at Jaguar, let me tell you, because it was much more cost-focused. But in our particular application, it was slightly different. So we'll cover through each of these briefly. First is this drop test. So that is an animation on the right. It's going to show you. This is what a good drop test looks like when it's a pass. Good, okay. It's still a pass from last time. But essentially what you have to do is take the battery. It's a rather morbid story of how you end up with a drop test, by the way. It comes from a rotorcraft fuel tank test, and it's done from a series of military real-life accidents. And they calculate the height at which they're confident you cannot survive, which turns out to be 15.2 meters. The idea being that if you dropped from less than that height, you would hate to survive the crash and then be set on fire by fuel tank or something else, all right? And it's exactly the same as a battery, okay? It is as horrible a story as that, but in fact, that's all you do in aerospace, is talk about different ways to stop people from being injured, is basically the essence. But you drop the battery, you can have something called an automatic service disconnect, so you can disconnect as you come down. Secondly, you've got to provide a manual service disconnect for those on the ground. And then there's 3 main things you've got to be able to comply with. One is fire. So you cannot have any fire. You can see on that particular video we didn't have any fire. Secondly, you cannot obviously electrocute anyone. And then thirdly, you have to ensure there's no release of toxic gases or materials, okay? And this battery makes it look very good, but it took lots of years to reach the point where we were comfortable at the mass point that we had and the performance that we had to be able to pass that drop test. Secondly, thermal propagation. So thermal propagation basically happens when a cell catches on fire. In our particular case, we make lots of the cells catch on fire, and it's forced on us by the EUROCAI, by the standards authorities. And it's kind of a good thing to force on, so make sure that we're robust on that. So we have in this picture it's 1, but in reality it's lots of cells we get to go at once. And a number of things happen. So that's one, the cell goes, and then a number of things happen. One is we use cylindrical cells, hence the reason I'm showing you a cylindrical picture. But the cell ignites, and then you've got a few things to deal with. One is you've got conduction of that heat to neighboring cells, because then the neighboring cell catches on fire as well. You've also got, it ejects out the top, so you've got gas, material, flames, whatever else, you want to get that away from the system. The third one is it can land back on. So inside the cell you've got copper that sits around the electrode. For the most part, the active material gets flamed away and you end up with a copper. And that copper can come out and short circuit on a neighboring cell. That can cause the next cell to catch on fire as well. And then the final one, in a cylindrical cell, you've got this pressure gap at the top. If that pressure gap operates, you're trying to force it out the top. Sometimes, if the pressure is too rapid, it can come out the side, and that's a much more different, so you end up with a slightly different condition. I wanted to show you some before and after photos of a successful battery test whereby I'm afraid to say that the individual that took these photos was not thinking of me presenting today. They were just thinking of getting demonstration for the test. So I don't have the exact same angle from the same point. But you can largely see the battery pack, you can see the battery pack remains intact. You can see a little bit of this black soot along the bottom on that after picture. That's essentially all of the stuff that got vented out through the vent. And so in the event that a fire happened when you were flying, the requirement is something called continuous safe flight and landing. You wouldn't even notice. The pilot would know there'd be something coming out the back, so I guess you could sort of crane round if you were paying a lot of attention. So you're going to continue safe flight and landing, you're going to continue to your destination or wherever else it is that you're going, and the requirement is just send all the thing out one designated vent. It cannot interact with the pilot, it cannot stop in terms of the passengers. You'd get your stuff, you'd walk away from the aircraft, then you'd go, oh, is that meant to be sort of smeltering on the side there? And that's exactly how it would pass. The other advantage you've got is, in aviation, certainly our vehicle, you have multiple of these batteries. And so when one fails, all of your failure conditions are dealt to deal with the fact that one of them has essentially caught on fire, this worst case fire condition. Okay, second from last is this state of function, which again includes, it's basically a state of charge. It's the little battery you've got in the top right of your iPhone, or other phones are available. But you're essentially looking for, and what you're trying to predict is the exact power and the time that power can be provided for the duration of the flight. So in this case, this is an eVTOL. You take off VTOL, you take off in your vertical configuration, you climb for a period of time, you cruise, you descend, and then you land again vertically. The dotted line is what you would call a go-around. So you're coming down to the landing pad, someone's pet cat's on the sort of landing pad, and you've got to go around and sort of find somewhere else. And that's what that condition's dealing with, which is this hover condition. We overlay onto that the power demand. So we have huge powers, and anyone that knows anything about batteries know that this power at the end is a massive headache because you're coming low in your state of function, your state of charge capability, but now you still want maximum power coming into land. So that's the condition you have to deal with. It means you set aside a lot of your battery permanently just sat there waiting for this failure condition, so you never operate that low. Finally, we end up with some profile in terms of the energy where that sits. So we see some cruise does consume the vast majority, depending on the length of the cruise. So your power demand, although very high during those vertical takeoff portions and landing, actually it's relatively reasonable in terms of total energy that it consumes. 1 minute, excellent. So the final thing is sample size. When you take a cell, progress onto a module, you start coupling these things together. Now anyone that's done some sort of physics at school will remember that multiple resistances inside a line, the minute those resistances vary, you can end up, in our case, producing energy in different quantities and at different powers, right? And the difficulty for that is, the minute that you start to scale up, here we go. So this is 300,000 plots of cylindrical cell data for you, okay? Resistances that come across the top. You can see that you might take a nominal value at cell, but the minute you put it into a module, you'll end up with a distribution in that nominal, right? So now I've got to deal with the distribution. That means every time I take power, some part of that cell is taking more power than another one. Which means that when we talk about lifetime and power, and that of course escalates up. You've got a whole fleet, you've got aircraft, and so this problem so every time that Chris and his team and Vertical try and deal with this consideration of what is the remaining time of flight, what's the power required, what does a thermal propagation look like, what you actually have to do is consider what does it look like if everything gets skewed at the top end, right? What happens if I end up with a battery where everything's very low resistance, very high energy? What's the condition that captures, and is it possible? And thank you very much. Thank you for your time.
Thank you. I'm being very strict about time so that we get enough time for the panel discussion. So let me introduce our third speaker. So Professor Lee Johnson is Professor of Electrochemistry. So remember I said electrochemistry, basis of batteries, back to Faraday, at the University of Nottingham. He got his PhD in physical chemistry and electrochemistry at the University of Nottingham, and then he went to work for Peter Bruce and his group in the University of Oxford, which is one of the teams that's been very, very involved in battery development, and he studied the lithium oxygen battery. He then went back to Nottingham to become a research fellow there and received a very prestigious EPSRC fellowship in 2018. And from thence, he's become associate professor and then professor in the School of Chemistry at the University of Nottingham. I know he's an absolute expert on all types of batteries, but particularly lithium-ion batteries, lithium-sulfur batteries. So over to you, Lee.
Thank you very much. So, yeah, I'm going to tell you about the kind of batteries that might push the envelope a little bit in terms of electric flight. So I think I am, perhaps, I'd argue this is already a very optimistic few presentations we've seen, right? We're trying to take batteries and put them in the place of a fuel where fuel is basically free and amazing. But I'm going to try and show you how we can power full commercial flights, or maybe how we might in the future. I think my optimism is expressed by my image. Okay, I'm going to make this amazing, definitely not AI-generated image of a green plane. It's going to fly on a bed of leaves, and it's only going to leave green landscapes behind it, right? So this is where we're going to get to at the end of the talk, okay? But let's get back to reality a little bit. We're trying to compare a battery to a chemical fuel, an oil, right? So something in a beaker, you can see it up there. And the problem with that is, a chemical fuel has a huge amount of energy in it. So think of there 40 megajoules per kilogram, compared to a battery, which is on the order, and I've gone for a lithium-air battery here, about 2.5 megajoules per kilogram. So just consider that for a second, right? That's an order of 10 difference in energy density. It's an incredible challenge to overcome that. Why would you ever put a battery in a plane? If you had the option, you would not, right? The reason we don't have the option is if you look at the plot below, where you can see the two blue plots, what you can see there is the energy efficiency of taking the energy from a wind farm and turning that energy on the left into a synthetic fuel, where first we have to electrolyze CO2, let's say, then we have to do some chemical steps to it, then we have to transmit it, and we have to put it into a combustion engine. And as a chemist, let me tell you, every time you make a complex chemical transformation, you are going to lose a lot of energy. Anyone who tells you otherwise is lying. It's inevitable, right? Complex chemistry changes always lose energy, or you have to put a lot of energy in, right? Whereas a battery, that's the plot on the right, batteries are simple. They have to be simple because we take energy in and out of them hundreds, if not thousands of times, and therefore they're incredibly energy efficient. So while a battery has 10 times less energy density, it has roughly, at least compared to this e-fuel I'm comparing to, about 10 times more energy efficiency if we consider wind farm to kinetic energy powering your plane. Now, we can argue with the numbers, we can take different fuels, but the result will always be broadly similar, right, that the battery will be more efficient. And you can see the number of windmills I've got at the bottom kind of expresses that in a kind of schematical way, right? So that's why we might want to use batteries. And that's not to say we wouldn't use the chemical fuel, it's just a question of when we would flip from one to the other. So let's consider when we might do that then. We've already seen that the eVTOLs can be powered by lithium-ion, and they're comfortable with a lithium-ion battery with a lithium-ion battery pack, and I'm talking about pack, that is all the cells assembled together, not the cells themselves. You can get around 250 watt-hours per kilogram, maybe 250, maybe 300 watt-hours per kilogram for a lithium-ion battery pack, but nothing beyond that. And even that's with advanced lithium-ion. And if you look at the plot, you can see that, yeah, we can power these taxi-type planes with that, maybe even edging into regional. But if we want to go to full commercial flight powered by a battery, we have to be tipping into the 500 watt-hour per kilogram, if not up to 1,000 watt-hour per kilogram energy densities. And just to be clear, I'm focusing here on energy per weight. There's been a bit of discussion about the automotive industry today, and to be clear, the automotive industry doesn't really care about energy per weight. It cares about energy per volume, and it cares about price. And that's why the batteries have pursued those metrics, not energy per weight, and we need to turn that around a little bit. So the real question for us then is, if we want to hit these kind of metrics, and we want to, let's say, power a narrow-bodied plane, we need to be finding a battery that's going to give us around 700 watt-hours per kilogram. Can we ever do that? That's the question I'm going to kind of present here. Now, I'm a chemist. There's going to be no, I apologize, no fancy pictures of plane here. I'm just plain, so I'm just going to have pictures of chemicals, right? And I'm going to start with this one where we consider what's in a lithium-ion battery. And at least at the positive electrode, what we've got is a lithium cobalt oxide, or some kind of metal oxide. And metals are intrinsically heavy, right? Just based on where they are in the periodic table, they have a large mass. And what we need to do, if we want to make a light battery, is to find something to store the charge on. Rather than storing the electrons and the charge on the metal, we need to find something light. And the obvious thing is to go to the top right-hand side of the periodic table. We might pick fluorine, but that will be a problem because fluorine gas will just disappear from the battery. But then we could come back to reality a bit, and we could maybe think of oxygen. Can we store the charge on oxygen? Can we give the electrons to oxygen and bind a lithium ion to that? Or maybe sulfur would be an option, right? And then we're going to drop quite a lot of our mass compared to if we were using cobalt. So what would that battery look like? And that's what I'm going to present today, is the lithium air battery. This is an air-breathing battery where instead of storing the charge on cobalt or some heavy metal or metal oxide, we're going to store it directly on the oxygen. So we're going to use a lithium negative electrode. We've got to use lithium for the voltage. There's no high-energy battery going to not use lithium. That's just a fact. Oh, if my thing will work. We'll have some kind of electrolyte, which will be organic, and we'll have lithium ions in it. We need electrolyte to move the charge around in the battery. And then we'll have some kind of porous positive electrode structure where we're going to do an oxygen reduction reaction. This is somewhat similar to a fuel cell, if anyone knows about a fuel cell, although the chemistries are widely different, but you can take that analogy. And we're going to reduce oxygen and give it 2 electrons and 2 lithium ions to form lithium peroxide. I'll come back to why we want to form lithium peroxide later and not an oxide. But the peroxide is a solid, and it's going to fill up the structure within that electrode. We're going to fill that whole volume, and we need to if we want a high-energy density battery. And then what we're going to do is reverse that on charge. We're going to oxidize our peroxide, kick our oxygens back out. Now, our lithium ions are going to go back to the anode, to the negative electrode, I should say, and everything is good with the world. But the battery doesn't look quite like that. It actually looks like this, where it's actually a full system. So the big brown cylinder you can see, that's the pack. The pack is the assembly of all the cells. I previously showed you one cell that has many cells in it. But it's an air-breathing battery. We need to take oxygen from the atmosphere and pump it into the battery. So it has a whole series of engineering solutions on top of it that allow the battery to have that oxygen flow in and out of the battery. And give or take, modelers predict that this battery would give around 500 watt-hours per kilogram of energy density. So just enough to teed into that kind of area where we might get some meaningful commercial electric flight for the general public, okay? But I'd argue not good enough. There are also huge challenges. I'm not going to go through them all today. I don't have time. I'm going to cover 2 very quickly and then come to some engineering points to finish. But there's big problems with using reactive lithium metal, but that's for all future batteries, and there's a lot of degradation. But I'm going to focus on these 2 first. One, lithium peroxide formation, which lithium peroxide is an insulator. I'm an electrochemist. Me and insulators don't get on, but I want to give it electrons and it doesn't want them, right? And the other one is that we need to get rid of water and CO2 in the air. So let's take a look at those 2 problems. So the first one is the water. It's an air-breathing battery. So we're going to take oxygen from the air, it's going to go in the battery, but that's going to bring water with it. And the problem is, water will catalyze this process here. Sorry, I know we can't see the cursor on the camera. It'll catalyze this process here, I should say. So we want to form peroxide where the oxygen atoms are stuck together. And the reason for that is, as I said, battery chemistry has to be simple. If it's not simple, you can't make it go back the way it came. It wants to go backwards and forwards for the reaction hundreds, if not thousands of times. But if you put water in it, those 2 oxygens that are stuck together in the peroxide, they break apart to form hydroxide. And now you're into the territory where what you need is catalysts, extra energy, and a whole host of problems, right? So basically, you haven't got a battery anymore. You've got a secondary battery. It's just a primary battery. So what we found, though, is if you take out the steel and the kind of random catalysts from the battery, we can avoid this reaction. And actually, our battery can breathe air with water perfectly well. And now, if you come back to the engineering point, we don't need to take water out of the battery. We can allow that in and out of the battery fine, neglecting the lithium. I'll take comments on that, I'm sure. And that gives us a significant overhead or a significant increase in the energy density. And you can see the performance on the right there, but not too important. So that's one point. And I guess the point here is that with careful materials and chemical engineering, we can overcome some of the limitations of this system. The other point is that lithium ion has had 40 years of optimization. Right? It's been optimized to give you the perfect battery that you've got in your phone right now. And if we look in the top left, what you will see is a schematic, or a slice through a lithium ion cell, where those little circles you can see are the cobalt oxide. That's the active material that's storing the charge in the battery. And if you compare that to the schematic on the bottom left, you see that's a discharge from a lithium air battery. And what you might notice if you take a look is the lithium air battery doesn't have much material in it. We discharged it, but we didn't fill the space with the peroxide, the material that stores the charge, or if you want, it's not directly the energy, but we need it to get high energy. So in terms of optimization of this chemistry, we're far from what you need to achieve for lithium ion. So what we've done here to try and improve this is to develop molecular catalysts, which we put into the battery, which allow us to overcome, one of the reasons for this is that peroxide, as I said, is an insulator, and as you form it, what it can do is effectively passivate and stop the electron transfer events and make the battery low energy, effectively. We can't transfer the electrons because we're using this insulating material. So what we've done is introduce small molecular catalysts which effectively short-circuit this reaction by transferring the electrons from the electrodes in the battery to the oxygen, so we don't have to have this insulating barrier that we had before. The other problem is oxygen transport. Imagine that we're filling this up with peroxide such that all the pores are full. There's nowhere for the oxygen to get into this battery, and this is an air-breathing battery. Okay? We need oxygen to flow in and out. But if we fill it up with a solid, effectively, that's not going to happen. So what we've done there is introduce, effectively, polymer channels. These are polymers that introduce, you can think of it as highways for oxygen that run through the battery that allow the oxygen to get in and out efficiently as we form these solid materials. And the result, when we add this new chemistry into the battery, is when we discharge, rather than getting the empty structure that you can see on the top left, where we haven't really stored any charge, we haven't really got a high-performance battery, we've got the structure you can see on the top right, where now all of those particles that are filling up the structure, that's the lithium peroxide, and that's giving us the kind of energy density that we need to make this battery really work. And we can now achieve a 40% filling of the battery structure with lithium peroxide, which is the kind of numbers that you have to hit at a cell level or an electrode level if you really want a battery that could hit 500 watt-hours per kilogram or higher. And there's still work to do on the engineering, but certainly a fairly big step forward in the performance there. And if you look here, this is our general cell performance. You can see we can now, electrode performance, we can kind of hit double, if not triple, the performance at the electrode level compared to lithium ion. And that's going to be critical if we want to translate that into a workable cell. So I just wanted to I was highlighting those two kind of chemical points, but I think it's also important to note that this battery requires a whole host of expertise to really make it work. It's also got massive engineering challenges. And I think that's probably the one where it's most important when we start to think of aviation. So if we take the chemical improvements we've made and we reconsider our modeling, we think we can probably hit a battery of around 600 watt-hours per kilogram. As I said at the beginning, pretty good, but it's never quite going to get us into commercial flight type of territory. So how do we make that last step, given we think that might be the best we could ever achieve just by optimizing the battery? Well, the reason we think we can improve it is our optimizations thus far, as I said at the beginning, are really motivated by the automotive industry. All of the modeling and designs of these batteries are motivated by the automotive industry. Well, we're making a battery which will sit in your car and then sit on your drive. And that means everything that is needed in that battery has to be inside of your car, and you have to be able to use it simply and efficiently, etc., etc. But that's not how planes work, right? That's not how an airport works. So we consider, here's our overall system. This is our battery with our gas handling. There's an opportunity here to take advantage of the plane and the airport in general, and note that this is a kind of a change the business model effectively, where instead of having this as part of the battery, we start to integrate this into the plane. So for example, to operate this battery, we need to have a lot of pressure, a lot of gas flow, a lot of heat management. But in your average plane, there's a lot of flow of air, there's a lot of hot and cold air. We can integrate these things, And a lot of the extra weight that makes up the system of the battery can be added, can be shared with the plane, and that can give us a significant boost. Yeah, no problem. The other one then is that if you think about putting this battery into a plane, I said a lot of the system engineering that goes into the battery is for removing CO2 and water from the air as we feed this into the battery. But if you're at high altitude, the humidity is near zero, and we think we can make the battery tolerate quite a bit of water anyway, so that can be effectively removed from the whole system, and that again gives us an extra boost in energy density and shifts the performance of the battery. And then the final one is that a lot of this technology here, a lot of the kind of system, is integrated there to regenerate the battery. So when you stop and you charge, in a lithium-air battery, you don't just reverse the electrochemical reactions, you also regenerate the scrubbers and the materials that go into the gas handling system to allow you to run the battery. But here, we wouldn't actually put them on the system. We would just leave them in the airport. There's no need to fly with all of that. Just leave it behind. And when you go to the next airport, you've got a new system. And if you take all those kind of engineering considerations into account, we think we should be able to get to around 700 to 900 watt-hours per kilogram, which is kind of that number that we need if we really want to power a wide-bodied flight. So I think I've maybe simplified this. There's definitely huge challenges, both chemical and engineering. But I think if you consider the roadmap to the technology, there is a solution there that could meet our needs. Excuse me. So just to conclude then, I work with some fantastic colleagues. Some of them are actually in the audience here today. They snuck in. But in particular, I just want to thank Professor Graham Newton and Professor Darren Walsh, who I work with at Nottingham, and indeed all of our team at Nottingham. That's one of our more recent pictures. And as mentioned earlier, I work closely with Professor Peter Bruce on this technology, plus a whole host of fantastic collaborators around the world on development of the lithium-air battery. And thank you for your attention.